Okay, so this is, like Chloe asked, this is the second lesson. And what we're going to do today is mathematically analyze reaction rate, just like we did before. But this time we're going to use something that's called the rate law. So those of you that are taking calculus right now will recognize that a lot of calculus is talking about rates of change. You do average and instantaneous rate in functions, but chemistry and calculus have a lot of connections. Some of you I taught math, right? So there is a lot of mathematical connections to chemistry, and this is a very, very good example of one of those cases. So when you drew, or we analyzed those graphs, all of them were exponential, none of them were linear. And what that means is if you don't have extensive advanced functions or calculus knowledge, then this kind of analysis can be a little bit different, a little bit difficult. So those of you that are taking calculus are going to take chemistry in first year university. You might do something called calculating the area under the curve, finding the derivative, and then eventually finding the integral, which is related to this as well. We're going to stick with a very bare bones analysis. You have to be given a bunch of data in order to do this. So if you have the note printed off, you'll notice that you're given a chart. These questions look very, very unique, okay? So that's good. So it is the shape of a concentration time graph. We saw that was exponential. So in the questions in Thursday's note, all of them were decreasing, but you could have increasing graphs as well. That doesn't matter, okay? But the big thing is it's exponential, it's not a straight line. Which makes a lot of sense. If we are talking about a reaction, we usually think of you put the reactants in and you make some products. So initially, when you start a reaction, there's a lot of reactants. So if you calculate the rate of a reaction, at the beginning of a reaction, it's going to be very, very fast. There's a lot of reactants available to react to make the products. As the reaction goes on, if you calculated an instantaneous rate later on in the reaction, the lines start to level out or plateau, then you're not going to get as fast a rate because the reactants are gone. There's just less reacting. Okay, so it can't be linear. So when we write a rate law, it is going to be, we're only going to be concerned about the reactants. So in my random example here, I didn't even put a product because we don't care. So it's always rate equals K, which we'll talk about in a second, times the concentration of however many reactants we have. Usually it's 2, sometimes it's 1. The maximum you can have is 3, which we'll talk about on Friday. So it's usually 1 or 2 or 3. And it's going to be raised to some exponent, m and n. For now, we'll call that, or we'll use those to represent the general exponents, and that's our job today. How do we find what those exponents are going to be, okay? And just like we did with average and instantaneous rate of change, the square brackets represented concentration. Concentration is a very easy thing for us to measure, so that's usually what we're going to do. So the same thing will apply here, okay? So we're going to calculate the exponents, and we're going to use that to help us tell stuff about the reaction. How fast is the reaction going to go? So if we have Mrs. Todd's chemical factory, and I need to make the reaction as fast as possible because I want to make as much money as I possibly can, then I need to look at what the order of reaction is for my reactants and figure out which reactant is going to give me the most bang for my buck, basically. Okay? Same, there's something also called the rate constant, which is K, also determined experimentally. So that means we need that chart of data to do it. And since it's all multiplying, the larger the K, the faster the reaction. So then the smaller the K, you'd be multiplying by a smaller number, the smaller the rate. So we're going to find or calculate the exponents, we're going to calculate what K is, and we are going to calculate what rate is. Okay, so if you have a rate law, then each exponent in the rate law is called the order of reaction. Which is sort of unfortunate because it doesn't mean the order that the reaction occurs in. It means how is that reactant affecting the rate. It's how is its concentration affecting the rate. You can find the total order of reaction, which is adding them all together. So generally that would be worth 1 mark, very few marks. So you can do mathematical questions with these, find the exponents, calculate the K, add the exponents together to get the total reaction, and you can use the exponents to predict the rate. If I change the concentration of reactant A, thank you, how does that affect overall rate, etc. So that's what we'll do first. And then we'll look at the larger chart questions. Okay, so you can be given, or you can have questions where you are actually given the rate law. Okay, so this time it's got the same general formula, rate equals K. It's got concentration, there must be reactant A and reactant B, but it tells you that the exponents are 3 and 1. So that means that the order of reaction with respect to A is 3. The order of reaction with respect to B is 1, and the total is 4. And so this is an exponential function. It's the concentration of A raised to the exponent 3, or cubed. So that has a much larger impact on the rate than raising something to the exponent of 1. And if this kind of math messes you up, you can just test it out in your calculator. What is 2 to the power of 3 versus 2 to the power of 1? 2 to the power of 3 is 8. 2 to the power of 1 is 2. That is not, or that is raising something to the power of 3 has a much, much bigger impact on the rate of reaction. So you can do questions like this, where it doesn't give you what the concentration is, but it tells you how it is being affected, okay? So it says, if you doubled the concentration of B, how would the reaction, how would the rate, or sorry, this one, yes, how would the rate of reaction be affected? So you don't know what B started at, so we're just making an estimate. But you can use You can like plug numbers in if you want to. You can sort of plug numbers in, or you can just think about it logically and write statements too for this kind of question. So we can even pretend that B started at 1. So if you double it, we'll just put a 2 in there because it doesn't really matter. It doesn't tell us what it started with. So if we double the concentration of B, because it's to exponent 1, which is linear, that means then the rate is also doubled. Even though we don't know what A is, it's all multiplying. And when you multiply, the order doesn't matter. If this is 1,000,000 and this is 1,000,000, you're still multiplying it by 2, right? So if you double the rate of B, because it's to the exponent 1, the rate will also be doubled. Essentially that answer, both of those statements are identical really. One's a little bit more mathematical. So you kind of have to decide how far you want to take it. What is your math knowledge? How comfortable do you feel about it? Because this is fine. Doubling B doubles the rate. All you would have to do is 2 to the power of 1. That would give you an answer of 2, and that would tell you what would happen to the rate. Versus the next one, if you quartered the concentration of A, so A is not a linear change, so you actually have to do some math here. So 1/4 cubed, you cube the 1 and cube the 4. So now this time, it's up to you again. It's still multiplying, but when you multiply by a fraction, really what is happening to the rate? Is it getting bigger this time? No, it would be decreased or divide, right? This would be the same as saying divided by 64. You could write it as the rate would be changed 1/64. That's fine too, but lots of students don't love fractions. So you can think about what this would mean is that you would be, this line means dividing, right? So you would be decreasing the rate or dividing the rate by 64. So that's obviously a lot bigger. So even multiplying by doubling the rate, you know, the same change in concentration, that's fine. But now if you change the concentration of A, you're having a humongous impact on the rate. So then as a scientist, if we wanted to make our reaction happen faster, A has a bigger influence on the overall rate of reaction. How do we know that? Because it has a higher order. So even though it seems so simple to say, well, the order of reaction is just the exponent, but yes, it is, but it tells us something about that reaction. So then this would even carry into, say, like limiting reagent questions. So lots of times, especially grade 9 and 10, even grade 11, limiting reagent is a very specific topic. Which one gets used up first? Then if you had this reaction, we would want to make sure we had enough A. So we would set up the reaction to have a lot of A, so the reaction goes as fast as possible. And that's something that you probably for sure, we haven't considered before. So even though you just come to a class, you do the lab, there are plenty of things going on in the background to make sure your lab is as successful as possible. Obviously, we only have 75 minutes. Can you guys do a reaction that takes longer than that? No, even has to be like 30 or 35 minutes would be the max, right? Okay, so you can do this kind of thing if you're given the rate law, but how do we find those exponents? So what we're going to do is something called the initial rates method. And even if you forget that name, really the distinguishing feature will be you have to be given experimental data. So what this is saying, and you can be given a reaction, but you actually don't need the reaction. What you need is this data here. And so what's happened is a scientist has run this reaction. Sometimes this might be called the trial. So how many times has the reaction happened? And they did different measurements. The first reaction, they put in 0.4 molar, 0.1 molar, and this is the rate they got. The second reaction, they did 0.4 again, but then they changed the hydrogen, and this is what they got, a faster rate. This time, they greatly increased this, NO, and the rate also greatly increased. So instead of just saying, oh, it greatly increased or whatever, let's figure out how it increased. And again, you're only given information or data about the reactants because that's what we're going to use to write the rate law, okay? So these are both reactants, the reactants. And so that's why, because we don't really care about the reaction in the sense that we don't care what the products are or whatever, usually these questions don't have a reaction given to you. We just give you the data, you look and see what's in the row, the heading, to find out what you're going to write. Lots of times we just use A's and B's, like it's random, because it really doesn't matter. So what I'm going to do for the first one, I'm going to put the procedure on, I'll put the procedure on the left, like the steps, what I'm doing, and then I'll actually do those steps for this data. And then the second example, I won't write out the steps anymore. I'll just write what you would put on your paper, okay? And of course, we are eventually trying to write a rate law that looks like this. We put rate, then you put K first. It doesn't really matter because it's multiplying. Most students just go in order that you're given them. And we are trying to find the exponents. Okay, we don't know what this is, and we don't know what this is. So if you have it printed off, I think there's quite a bit of space there. My next slide has the data chart on it again. If you're writing it out, you don't need to write it out again. I just obviously can't fit anything more on this paper. Yes. Okay, so we have 2 reactants to look at, and we're going to look at each one separately. So I'm just going to go in order that the chart is. I'm going to start with NO, but it doesn't really matter, okay? You just can't do them both together. You have to look at NO, find its exponent, and then look at H2 and find its exponent. So if we need to consider the data for each separately, and we need to find the exponents separately, then that means that both of the substances can't be changing, or the rate, we can't figure out which one is influencing the rate and which one isn't. Okay? So for example, if we're going to do NO first, between run 1 and 2, is it changing? No. So that doesn't help us. Between 2 and 3, is it changing? Yes. And this example, we're just going to go consecutively according to the chart. The next example, we're going to do like 1 and 3. It doesn't matter necessarily the order of the runs. It's just random. They randomly did the reaction 3 times. Okay? So if we want to do 2 and 3, I like that. It changed. But then you have to check over here and make sure that this one is not changing, which it's not. Okay? And in fact, what people will do is, and this is unfortunate because the homework's from the textbook. If you go to look at the homework, you might find that people have done stuff like this. They'll have written in the book on the chart. So before you start the homework, if you have an eraser, try to get rid of those pencil marks or cover them up if it's in pen or something, because you don't want them to influence your answer. Who knows? They might not even be right. Once you do a few of these, you might do step 1 and 2 together. So when you're looking at is NO changing, we want to be quantitative. We need to know how much it's changing by. So you might do that at the same time. NO, instead of just saying changing, you would say the concentration of NO, what's happening to it. It's being doubled, okay? So you could write that at the same time. But I'll write it separately so you have a nice note. If you are not a fan of mental math, then don't do mental math. I don't judge, right? So all you would have to do is take the bigger number divided by the smaller number. And the good news is we want whole numbers. So if you do it upside down and you get a weird decimal, less than 1, then you know you've done something wrong. And you just have to flip it. So again, unfortunately, what you might see people do in your book is this, like they'll write it right on the chart, which is fine if you want to copy the chart out and do that in your book or on the test or whatever, you could do it on the test paper, but writing it in the textbook ruins it for the next time, right? Okay, so now we need to do the same thing with the rate. I did warn you about this. There is a significant amount of scientific notation. Okay, so try to get used to doing scientific notation in your calculator. So we have to do the same runs, 2 and 3. You can do the same thing. Perhaps you have a good grasp of math and you recognize that this is 4 times bigger than that. But if you don't, I don't care, just divide them. I don't care, I mean like I'm not going to judge. If you show all this math, I don't care. Okay, so again, because advanced functions is not a prerequisite for this class, that means that there are some of you that have not used logs to solve exponential equations. So this can definitely become more difficult. So those of you, again, that are continuing in chemistry or in math in university might find it more difficult. But for us, when you do this calculation here, these numbers have to be related. So if you you got a number 2 and then you got the number 5 here, then you have made a mistake. You've used the wrong trials. Because what we want to do is we need an exponential function. So you have to be able to write this number as a power of that. Okay? So usually it's like 2s or 8s, or 2, 4, 8. It'll be, or 3, 9, 27. It shouldn't be any like 256 or anything crazy where you're going to have to, go back to grade 3 and be like 2 times 2 times 2 times. That shouldn't happen, okay? It should be very, very, very obvious and that the two numbers are related. The next one we're going to do is 2 and 2, so the exponent will be 1. Remember, as much as I could make it whatever I wanted to, I want these questions to be practical. In a lab, would something have the power of 10? Probably not. Okay, so I'm not going to do that to you guys because that's not a practical calculation. Okay? Okay, so again, this is pretty wordy, and what you might find people do is they'll even just write it right in the chart, okay? So we need to write this number, the factor the rate's changing by, as a power of 2. So what that means is we want the base to be 2, and we want our answer to be 4. So we need to figure out what exponent we can use to get to 4. So if you do not love exponents, then you'll have to do the 2 times 2 equals, or you can start with 1. 2 times 1 equals 2. 2 times 2 is 4. Okay? So then 2 as a power of 2 to the power of 2 gives us 4. So we want this as the base, and then this is the answer. So you might see people just do this, like right in the chart, which is fine. And again, why do we care? Why can't we just leave it as 4? Because we want to write our rate law using exponents. We don't want to just write 4. We want to be able to plug in any concentration and find out how it affects the rate. Okay? Actually, I'll use the same colors I did. So for H2, I'm going to use the same numbering, but I'm not going to write the black steps, okay? And you know what? I'm going to combine 1 and 2. So for H2, now we need to decide 2 runs where the NO is not changing, but the H2 is. So that's a little bit, it's easy. Oh, it's the first 2. Wonderful. Yay. What's happening to the concentration? Yes. Or what's happening here? But how much? Yeah, doubled. But again, just divide them, okay? In fact, usually, often students won't write the one that's not changing because who cares? But just so in your note you have it nice and complete, that the concentration of H2 is being doubled and the concentration of NO is not changing. So then we can figure out at what's happening with the same trials or runs with the rate. (2.2) times 10 to the negative 5 divided by 1.1 times 10 to the negative 5 is also 2. Okay, so then we're going to do the same thing. And usually, so we're going to write 2 as a power of 2, which means 2 to the power of 1. When we do math, you don't have to write the 1, but sometimes when students do these kinds of questions, they do write the 1 to really emphasize what's happening. But it's up to you, okay? So we need to write the 2 as a power of 2. So 2 to the power of 1, which you can check in your calculator that you are right. And now please don't forget to write the final answer. We were asked to find the rate law. You found the exponents. So don't forget to do the rate law, okay? The final answer. And the general form, now, so we already wrote the general form. Now all we have to do is put in the numbers we just found. So it's always the same. Rate equals K. Every rate law should look like that. And then we found NO has an exponent of 2. And H2 has an exponent of 1. So once you have the rate law, then there are other things you can do with that rate law. We can plug in concentrations and calculate a new rate, which is why this is useful. We can also solve for what the rate constant would be. So finding the value of K is not that big of a deal. It's basically plugging it numbers into an equation like you did in grade 9 math. The only weird part is finding the units for K. And sometimes students get really, stressed out about this, but it's literally like 1 or 2 marks ever on the test. Okay, so it's not that big of a deal, but it is a little bit weird. So what we are going to do is we are going to use data from any of the runs. Most people just use run 1, but you just have to make sure that you use only one run. Like you can't do this value, and this value. It has to be the concentration and the rate from the same run. So you can, again, sort of decide how you want to solve for this. Maybe you like to rearrange before you do any math. Maybe you want to figure out what this is and then divide. It's kind of up to you, okay? K is our unknown. It's our x. So you have to do 0.4 squared times 0.1. And we need to have appropriate units. So this is where the trick or the trickiest part to K is. So if you have something, so this means mole squared, liters squared, times moles and liters. So if you have x squared times x to the power of 1, what do you do with these exponents? You have to add them. So then we're going to divide. When you divide, then you subtract. Okay, so adding and multiplying go together, subtracting and dividing go together. Okay, so how do we deal with this? Moles per liter second divided by moles cubed, liters cubed. So if you're asked to calculate K, and the next example you're not, so you don't always have to, but you have to figure out the units separately every time. So I'm going to do that at the side. I'll even make a little box here. Maybe I'll do a better job. Okay, right now this is what I have. This is a lot of lines, so you can rewrite it like this if you want, make it a little bit easier for yourself. If you divide fractions, you have to multiply by the reciprocal. And now you can start crossing stuff out. So this mole will cancel one of these. This mole liters cancels one of those liters. Nothing cancels the seconds. So the units will be liters squared divided by seconds times mole squared. This is nasty and not worth a lot of marks. Okay, so just do your best, give it a try. When you get a question like this, what's the order of reaction with respect to each substance? If you're not sure you did the rate law right, just again, this is an opportunity for you to get 3 marks. That if you, as long as you carry your mistake through all through the question, then you wouldn't lose marks again, okay? So we've said, what's the order of reaction? All you have to do is state the exponent, right? So NO has an exponent of 2. H2 has an exponent of 1. The total, like add total, you add them up. And you could just write 3. You don't need to write 2 plus 1. Okay, I'll figure out what you've done. This is a really beefy question, right? So there would be at most one of these on your test. So it's not like every single question is going to look like this. So the next example is exactly the same, except I'm not going to do consecutive runs so that you can see what that kind of question looks like. Yes? Okay? So we're given a new chart of data. This time we're given 3 reactants. That's fine. I'm just going to go in order. Okay, so IO3 is pretty straightforward. I can do the first 2 because these 2 are not changing. But then when I go to do, say, I, then now you have to check 2 of them, okay? But you're just looking for 2 rows where it's not changing. So it's not so bad. You just have to be careful. So for IO3 we're going to do 1 and 2. Point 2 divided by 0.1 is 2. One times 10 to the negative 3 divided by 5 times 10 to the negative 4 is also 2. So you might be like, oh my goodness, it's the same sort of factors. Yes, you have to be able to write this as a power of that. You have to. And like I said, some people will even just start to do it on here. Like they don't show any of this work at all, which is totally fine. Oh, I should write. Okay, so, and you can also use information from your other ones. We cannot do trial 1 and 2 because we just said it wasn't changing. So now we need to look where it is changing. Here and here, but we can't do that because that's also changing. So that doesn't work. Here and here, it's not changing. That doesn't work. So you could go in consecutive order or rows as well. So you could do this and this, 1 and 3. You could do 1 and 4, but we just have to check. So if we do 1 and 4, that's not going to work because the concentration of H plus is changing. But if we do 1 and 3, this one, IO3, 0.1, 0.1, that's not changing. And then H plus, 0.1, 0.1, it's also not changing. And when you do 0.3 divided by 0.1, you get 3. So that means that the rate must be changing by a factor of 3. 3, 9, 27, okay? And the more you use scientific notation, then it can help you sort of understand what your calculator is saying. This is 15 divided by 5 is 3, okay? But again, you do not need to use mental math. Use your calculator every time. Okay, so now we have 3's, but that's okay. 3's are also related. They can have the same exponent. That's okay. They could all have the same exponent, whatever. So now we know we're not going to use 1 and 2, and we're not going to use 1 and 3. So as you go along, you can check less each time. This one's also another obvious one, more obvious one, because it's a consecutive one, but that doesn't matter. These two not changing. This one is changing. You can streamline your answer because we already did this over here, or just do it again. That's fine. Okay, so I got a 2. So again, okay, when I do the rate, that means that my number should be a factor of 2. 2, 4, 8. Okay, and again, please, 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 please don't do all of this work and then not write your final answer, okay? So the homework for this, when I eventually give you a test review, it's going to say on the test review, if you did not do the homework for 6.3, go back and do it now. It is vital that you know how to do this. It's not that it's difficult, it's just that, sometimes people rely on formulas or whatever. This sort of is a procedure. You have to really try to do some of these questions. And what you'll notice is there are similarities. There should be common factors and things like that that you'll see over and over and over again, okay?